Okay, well, welcome back to MI260 lab session. This is the lab session where we will cover the modeling of using WinBUGS to fit network meta-analysis data. So what I plan to cover today is we'll quickly review the example that we went through in the lecture last week, including the network meta-analysis model. And then we'll step through the WinBUGS code to fit that model to the remission data that was published by Ramsberg and colleagues. And then step through any additional plots and outputs that we can generate from the statistical, from the WinBUGS code. I just want to ask if, are folks able to hear me okay? If you could just answer in the chat box. Okay, so we will work through the example and work through the WinBUGS code for this example and the related outputs. And if you have any questions along the way, feel free to go ahead and post those to the questions box. So if you remember from our lecture on Monday, we were working with data from this study by Ramsberg and colleagues on a network meta-analysis of the cost of antidepressants in primary care. The original network meta-analysis had 73 studies, and the studies were laid out in this sort of network of relationships, where all of the treatments were compared to venlafaxine in at least one study. And so because of that, for structure of the network, it makes sense for us to use venlafaxine as the comparator treatment in our network meta-analysis. And what that means is that we'll estimate differences from venlafaxine as our fundamental parameters in the model. And from those fundamental parameters, we can infer differences between all of the other drugs in the network. As we said in class last week, this one study from reboxetine, for the purposes of our analysis today, I'll exclude that one study. And so we'll be working with 72 studies on 9 treatments. And this was a little snapshot of the data with all of the studies that we have in this particular network meta-analysis having only 2 treatment arms. It turns out that the authors actually had placebo-controlled studies in their search, but for whatever reason they chose not to include the placebo arms in their network meta-analysis. So while that's unfortunate, and it would be really nice to have the placebo data so that we could, at a minimum, look at the methodology or an application of using multi-arm comparisons. In this particular case, the code that we'll be working through is going to focus on 2-arm studies. So the model, as we looked at it for the Ramsberg data, looked like this. We have the number of remitters, which on the slides here will be denoted Y, and when we get to the WinBUGS code, we'll denote that by R for remitters. The number of remitters follows a binomial distribution with a parameter P, and the number of potential remitters being N. And I, in this case, indexes study, and J indexes treatment arm within the study. So because all of our studies have 2 treatment arms, J will either be 1 or 2. And the model for the logit of the probability of remission is mu I, which is the logit or the log odds of remission in the reference group in study I, plus delta ij, which is a random treatment difference or random log odds ratio that's centered at the population average log odds ratio between treatments TI1, or the treatment arm 2 in study I minus the effective treatment arm 1 in study I. And because of the consistency assumption that we're building into our network, or because the difference between treatment 2 and treatment 1 in study I is the same as the difference is centered at the difference between treatment 2 and venlafaxine in study I and the difference between treatment 1 and venlafaxine in study I. So these capital deltas are our fundamental parameters, and we'll have 9 of those fundamental parameters. Okay, and this between study variance then we assume to be tau squared. And because we'll be fitting this in a Bayesian context, we have some prior distributions, and we'll cover those when we look at the WinBUGS model. So let's go ahead and bring up that WinBUGS model now. Our bugs model looks like this, and I'll just put these two things side by side here so we can compare and contrast. Our WinBUGS model says the following. It says, let's loop from 1 to ns, which is the number of studies. And so I will be our index for study, just as it is in our statistical representation of the model. We put a prior for mu(i) as a parameter centered at the prior is centered at 0 with a variance of 1,000. And for the k's, which in the WinBUGS code here I'm using k to represent treatment arm instead of j, which was in the notes. But k will run from 1 to na of I, which is the number of arms in treatment or in study I. In this case, na of I is always 2 because we always have 2 treatment arms. But as you move to more generic code, you could have na be 3 or 4 or however many. And it can be a vector that doesn't all have the same number doesn't all have the same value in it. So we'll say then that the number of responders are in study I treatment arm k. That's just like our yij over here. Follows a binomial distribution with parameters pik and nik. And the logit of pik is equal to mu(i), which is that, again, that study-specific log odds of response in the reference group, plus delta ik. And delta I, by definition, delta I1 is 0, just as it was over here. And delta I2 is equal, or follows a normal distribution with mean MD in study I and reference 2. And in this case, this is a precision tau. So that's just this one line of code here. This one line of code here is the bugs representation for this line of code here. And so the only tricky thing to figure out really is how do we represent in WinBUGS this piece, the difference of the deltas. Well, what we'll define in bugs are these fundamental parameters. In this case, in bugs, I'll call them D, which will correspond to the deltas in our slide set. But the D's will be the fundamental parameters, the differences from venlafaxine. And so we'll have the parameter D in treatment, T, in study I and treatment arm 2, minus the delta for treatment T, for treatment denoted by T in study I, treatment arm 1. So what we need to do is, what you might recognize here is that we need to define some data elements that will define what treatments are given in arm 2 and what treatments are given in arm 1. And so in order to do that, let's look at some R code. And in fact, we'll do this right here in Windows. So we'll open up our R session. And we'll open up the code to fit these models. And so what I'll do here is I'll go ahead and read in the data. which I'll provide to everyone after the session today. I'm sorry, I apologize for not getting this out ahead of time. I meant to send it out right after the lecture last week. So we have our data set here, which looks similar to what we had in the notes. I'll look at this again so it's strung out a little bit wider. And so here we have our our drugs, drug 1 and drug 2. These come into R as factors. And so if we just were to look at the levels of these things right now, by default, R is going to order those in alphabetical order. So we have citalopram first and venlafaxine last. Because we'd like to use venlafaxine as our reference group, the way that the WinBUGS code is set up, it will need to have the venlafaxine have a treatment variable of 1. So what we'll do is we'll re-level the variable drug 1 and drug 2, so that there'll be factor variables with venlafaxine being the first level, and then we'll just arbitrarily replace the rest of them in alphabetical order. So citalopram will be 2, escitalopram 3, and so on. And we'll do that here by using the re-level function in R. So here we'll just, the lines of code that I just executed were essentially excluding that one raloxetine study. So in this particular line of code that's highlighted here, we'll be recreating the variable drug.1 to be a factor, using the values of drug.1 and the levels being here in this vector drug label of drugs to keep. And then we'll re-level that, making the reference level venlafaxine. So let's go ahead and run these lines of code here. And now when we look at our the levels of our new data set D sub, the variable drug 1, we have venlafaxine first and followed by citalopram. Whoops, I guess duloxetine D comes in there before E for escitalopram. Okay, I see. So we didn't, when I did the levels up here of drug 1, we didn't see duloxetine because presumably duloxetine was listed in there as only in the column for drug 2. Okay, so this is the data set that we'll work with. The way that we'll create our matrix of treatment indicators, numeric treatment indicators, the vector of the matrix T, is we'll just convert the factors into numerics. So if you remember in R, when we convert a factor to numeric, what we get is the number corresponding to that factor level. So venlafaxine will be 1, and citalopram will be 2, and duloxetine will be 3, and so on. So when we set up our BUGS data, and if we were to look at the matrix T, and let's just look at the beginning of that, first few rows. Oops. I see, I need a capital D there on my BUGS data. So this will tell us in study 1, the reference is group 5, and in this case the comparator is 1, which is venlafaxine. That's okay because we don't have to have these in necessarily in ascending order as our reference group. And so this will the difference between 1 and 5 is the negative of the difference between 5 and 1. So this is how our the first few rows of that object look, and if we look at the end of it, we'll see that we should see something different. And so the last few studies here, we have the different treatments 7 and 8. Here, this study has treatments 2 and 6, and so on. And the way that we've set up our input data is R is a matrix. The first column is the number of remitters in drug 1, and the second column is the number of remitters in drug 2. And is a matrix that has number of patients in the treatment arm 1 and the number of patients in treatment arm 2, and so on. And S here is just the number of studies. And A, in this case, is always 2 for the number of treatment arms. And then T is the number of treatments, which in our case is 9. Okay. So we can then define the parameters that we're interested in monitoring. Actually, before we do that, let's jump back over here to our BUGS code and look at the rest of the BUGS code. So what we've covered so far really defines the likelihood of the model. Plus, we've defined the prior distribution for the mui's. If we jump down to the bottom of this code, we see the prior distributions for the deltas, or the d's as I've labeled them in the BUGS code. And here again, we're saying that by definition, d1 is 0. And for the remaining 8 d's, or 8 deltas, we say those follow a normal distribution with precision 0.0001 or variance of 1,000. And here I put a prior distribution on the standard deviation being uniform from 0 to 5. Which, because we're working on the logit scale, standard deviation of 5 on the logit scale is quite a bit. So this, while may not look like a very non-informative prior, actually is a pretty non-informative prior on the logit scale. Or maybe it would be considered weakly informative. So the only other piece of code here that we'll look at, or that's in the code, is ranking the values within WinBUGS and calculating which of these are the best. And the way that we'll do that is we'll loop over the number of treatments. So again, we have 9 treatments. And we'll create this variable, call it RK for rank. And it'll be indexed by K, the treatment number. And essentially this line of code then ranks the treatments from 1 being the best to 9 being the worst. To do that, we'll utilize the function in BUGS called rank. And what this function does is it takes this vector d, which are our differences from venlafaxine, and it says, give me the rank position, or the number of components of d that are less than or equal to the kth element of d. So what this does is this actually puts 1 being the lowest, and the lowest d, or the minimum of the d's, and 9 being the largest of the d's. Because in this case a large value is better, we need to kind of turn, and we want to represent 1 as being the best. We just need to turn that around here by subtracting that BUGS rank from the number of treatments plus 1. So what this line of code then does is it gives us these ranks from 1 to 9 across the 9 treatment groups, 1 being the best and 9 being the worst. And then this variable best is just equal to 1 or 0. It'll be 1 if the treatment, the kth treatment, is ranked the best, if the rank is equal to 1. Okay. So let's go ahead and take a crack at running this. Running this in WinBUGS. So the parameters then that we'll monitor are the d's, or our deltas, our differences from venlafaxine, between study standard deviation in those differences, the rank of the 9 treatments, and the indicator for which is the best. Actually, an indicator variable for each treatment, whether it is the best or not. And we'll define a simple function here to generate our initial values. And then we'll fit 3 Markov chains. And we'll use a burn-in of 20,000 for each, and then a follow-up of 10,000 post-burn-in samples. And for this particular problem, that seems to be reasonably sufficient. So while this is running, let me check and see if we have any questions about the WinBUGS code or the model that we're using. No questions yet. So Bugs is cranking away here at our few samples that we're asking it to do. This should finish up here in about 30 seconds. So it's finished our 20,000 burn-in. Now it's monitoring the parameters that we've asked it to monitor and doing the last 10,000 updates. And then it's going to wrap up here in a second. So what we'll do with our posterior samples now is we'll look at making some inferences using the posterior samples, such as the pairwise comparisons in the deltas, the comparisons of the rank probabilities, and we'll really focus on those for our class session today. So WinBUGS is finished doing its part. If we are to then work with our object, we can print it. So if we're interested in looking at NMA fit, so here we have our very high-level summary of our differences from venlafaxine, of our posterior standard deviation, which to one decimal place has a median of 1, with a credible interval that goes from something less than 0.05 to something more than 1.5. We have our posterior summaries for the ranks and posterior summaries for this variable best. Of course, if we wanted to plot that, we could do that as well. And we'll get our credible intervals for the parameters D, SD, rank, and best, as well as the deviance. And we can see just from a quick glance at this that the intervals are generally comparable across all of the 3 Markov chains that we've run, giving us some sense that we are those three Markov chains are sampling in the same general parameter space. In other words, they've converged to the same, more or less the same spots. So in terms of making comparisons, the first thing that we'll do is we'll look at these pairwise comparisons of effects. And in order to make it's fairly simple to work simply with the posterior distribution to get those comparisons of effects, but I think it's oftentimes useful to put those in context of the data. And in order to do that, we need to reshape the data set that we have a little bit. And so what I do here with this little chunk of code is to kind of turn the data set around. So let me run this and then I'll show you what it looks like. Turn the data set around so that we have, for every drug, we have the number of patients on the treatment arm in that study and the empirical proportion of patients who were remitters. And that'll be useful when we try to get our simple pairwise meta-analysis effect and plotting the raw data. So what I've done here is I've just put together a short function that does that pairwise comparison based on a data set that looks like this. And so it the pairwise actually works on the raw data set, and it takes out the studies where we have either drug 1 or drug 2 is in a list of treatments that we pass in as input to this function. And then it just calculates the random effects meta-analysis. Here's our method equals REML, so random effects meta-analysis using the number of remitters and the number in the treatment groups as our input into that function. So this is just a little function that makes it easy to generate this kind of comparison for any two pairwise treatments. And then so if we were to, for example, interested in comparing, as we were in the class, sertraline and venlafaxine or sertraline and paroxetine, we can just pass these into this pairwise function along with the data frame that we want to make reference to, and it'll fit those. So if we look at, for example, fit 1 now, this is our pairwise comparison using the 5 studies from which compared sertraline to venlafaxine. And we see from that particular comparison, we have an I-squared of about 36%, which gives us some sense that there's a moderate amount of between study heterogeneity in those effects. And if we were then to plot that, it would look like this. So these are our 5 studies comparing sertraline and venlafaxine, and here's our random effects estimate of that. If we wanted to overlay on top of that the Bayesian credible interval, all we would do is simply extract from our NMA fit object in the Sims list component of that list, we take out the 8th element of the matrix D, the 8th column of the matrix D, I should say. And I know that I'm interested in the 8th column there because sertraline, if I look at the levels of D sub $drug 1, sertraline is the 1, 2, 3, 4, 5, 6, 7, 8. Sertraline is the 9th one there. All right. Oh, this should be 9. There's a little typo there. Sorry about that. So if I were to calculate the quantiles of the 9th column of the D's, the posterior samples of the D's, now calculate the 2.5 and the 97.5 percentiles. We'll just put those into an object called, oh, I'm sorry, that's why this is 8. It's 8 because there are 8 of these. The first one is 0, so by definition, WinBUGS isn't monitoring that because it's not a random element. So D1 is the difference between citalopram and venlafaxine, up to D8 being the difference between sertraline and venlafaxine. So I had that right to begin with. Sorry about that. Mistake on my mistake. And if you look at the difference D between sertraline and venlafaxine, we have a credible interval that goes from about minus 0.37 to positive 0.007 with a median of about 0.18. That's on the log odds scale. And so when we plot that onto if we were to overlay that onto our plot, we'd want to do a transformation using the exponentiation of that. So we'll just add that using the add poly function that we used back at the beginning of the class. And we see here sertraline versus venlafaxine. When we exponentiate minus 0.18, we get something that's about 0.83. Again, credible interval from 0.69 to 1.01. And we could do a similar thing then with the other treatments. We're interested in comparing paroxetine to venlafaxine. We can look at our posterior distribution for that. It goes from minus 0.31 to positive or minus 0.000035. And if we were to visualize the data, visualize the data relative to the and the pairwise comparison estimate relative to the network meta-analysis estimate, we have a plot that looks like this. If we are interested in looking just at the posterior distribution for the difference, let's say between paroxetine and venlafaxine, we can do that just simply by making like a density plot. We say plot density of Sims, NMA fit $sims.list $D7. This would be our estimate of the posterior density for the difference between venlafaxine. I'm sorry, between paroxetine and venlafaxine. And if we wanted to look at that on the, this is on the log odds scale. If we wanted to look at that on the odds ratio scale, we would just exponentiate that. And so here it is on the odds ratio scale. Okay, so that really covers our pairwise comparison of effects, looking either at differences in delta values. Oh, one thing I didn't do, these were both differences between venlafaxine, so we could work with our fundamental parameters directly. If we are interested in comparing two treatments, then we look at differences in the fundamental parameters. So if we are interested in comparing paroxetine and sertraline, we'd look at the difference between D8 and D7. And if we were to do that, make a similar sort of plot here, this is our one study that compared paroxetine and sertraline. In this case, because if there's only one study, we can't fit a fixed effects model based on that one. I'm sorry, we can't fit a random effects model based on that one study, but we can fit a fixed effects model, which in essence is just, it's not really doing any aggregation. It's just taking the estimates from that one model. Using the whole network now, we're using all of the potential indirect comparisons and all of the comparisons in total to estimate tau squared. So all of that added information shrinks the difference between these two from an estimate of 1.24 to an estimate of 1.03. Okay. If we wanted to work with the ranks, this is a fairly simple thing to do. One thing we might be interested in is just making a posterior distribution, or a histogram of the posterior distribution of the ranks. I use the bar plot for that because of the discrete nature of those, of that variable that we're monitoring. Right, the rank has to be an integer between 1 and 9, and so if we use that bar plot function to make a histogram of the a histogram of the posterior distribution of the ranks. We see here, this is what we saw in the notes. Venlafaxine looks pretty good. Citalopram ranks are very high, so this is not so good. Fluvoxamine likely to be the worst, but also moderately likely to be the best. So lots of uncertainty here in the rank for fluvoxamine. Fluoxetine, on the other hand, we're pretty sure it's not the best. Almost no chance it's ever the best. And we're pretty sure the rank is somewhere less than 5, for example. If we were interested in calculating the posterior distribution of the rank for each treatment, we could apply to this matrix RK that's in our sims.list output from WinBUGS. We could take the posterior 2.5, 50th, and 97.5 percentile, and that can give us the posterior credible interval for the rank for each treatment. And then we can put them in ascending order so that we can make a plot that looks a little bit nicer. So this shows us then here that as we make this particular plot, I just use the segments function and the points function to make these segments here from the 97.5 to from the 2.5 to the 97.5 percentile, and adding in the median as a red line for our various drugs here ranked from the best escitalopram. Sorry. This isn't right. Oh yeah, this is right. The best escitalopram to the worst fluvoxamine. This is ranked based on the median. Okay, so one of the beauties of working with WinBUGS for this kind of analysis is it becomes very easy to do this ranking and working with, and the ranking then is based on those fundamental parameters. The fundamental parameters follow or are inherent in this model and are related to that consistency assumption that we're making. In other words, we can define our model in terms of these fundamental parameters because of the the assumption of consistency or exchangeability. We could do a similar kind of ranking in a model-based analysis if we were interested in doing that as well. The last piece that I'll talk about in using our WinBUGS output will be calculating this, this notion of the surface under the cumulative ranking curve. And so in order to do that, we need to think about what does that cumulative ranking curve look like. And so let's plot out that cumulative ranking curve. Well, first I'll do the calculations and make the plot, and then we can come back and talk it through. So what I've plotted here for each treatment is the probability of being the best, and then the probability of being in the top 2, and then the probability of being in the top 3, and so on, up to the probability of being in the top 9, which for all of these treatments is 1, just by definition. And so that's what this piece of code here is doing. It's simply saying, give me the number of drugs that are in my that I'm working with. I tried to write this in a generic way that you could apply it to your own analyses later on. And then across those drugs, apply this function, and it would say then, take the ranks for that particular drug, define them as a factor that has levels 1 to p, or 1 to the number of drugs, and then table those and divide by the number of elements in my posterior distribution. So this then gives me a table that has probabilities of being ranked number 1, probability of being ranked number 2, and so on. And then we can use the cum sum function in R to calculate the cumulative probability. And that's what gets returned. If I were to look at this object sucra, it looks like this. So if I were to scroll up here, we would see we'll look down here in the lower left here for fluoxetine. In the graph here in the lower left, it starts out the probability of being the best is 0, the probability of being in the top 2 is 0, the probability of being in the top 3 is something very, very tiny. We get up to about 3% here, and being 5th best or better, and so on, up to being 8th best or better is 72%. And then what sucra is the area under this curve up to not being the last one, because the last one's always 1, but being up to in this case, the 8th best. And that's what this function here does. It just takes the sum of the cumulative probabilities up to the 8th and divides by 8. We're just averaging those cumulative probabilities. So it's not, we're averaging the cumulative probabilities. And then I just plotted that sucra value here as part of the title. And again, this is just one other summary measure, a way to sort of, if you're interested in coming up with a measure of what is the best treatment, this would be one way of coming up with that measure of the best. And this tries to get at some of that uncertainty, a large amount of uncertainty in the individual ranks themselves. And so if you have treatments that tend to be towards the top 1, 2, or 3, they're going to have high sucra values, even if there's a fair amount of uncertainty in what their actual rank is. Okay. And then the last little chunk of code we have here is just how to calculate what is the posterior distribution for being the best drug, or the one with the rank of 1, which is what's being calculated here. So across each of the drugs, we're calculating the mean of that best variable, or in this case, the mean of the rank being equal to 1. Which is 0 or 1. So when we take the average, that gives us a probability of being equal to 1. And then we just plot that here at the very end. Again, using the bar plot. So what I tried to step through here was all of the code to create the kinds of plots that we have in our in the slide set. So I think that's where I'll stop for the lab session for today, unless there are any questions. We do have one question here. What is the value of internals for ranks in comparing treatments? I think this means what is the value of intervals for ranks in comparing treatments? That's a good question. So the value, the way I see the value here, if we look at this, I'll make it bigger. We'll look at it here in R. I think for me the value is just showing that the large amount of uncertainty in those distributions. You can get at the same kind of thing by simply plotting the posterior distribution itself. But using the intervals is just one other way of displaying that. So if we were to come back here and look at these posterior or credible intervals, we can see, for example, that fluvoxamine and fluoxetine both have a median rank of 8, but the credible interval for fluvoxamine goes from 1 being the best to 9 being the worst, whereas for fluoxetine, we're much more confident that it's toward the bottom. In fact, with the credible interval going only from 5 to 9 being the worst. Similarly, for escitalopram, we're pretty confident it's in the top 4. So it just shows that how much uncertainty there is in the ranking. And you can see from any of these, duloxetine, mirtazapine, certainly fluvoxamine, citalopram, there's a lot of uncertainty. We don't have much precision in the ranks, which I think you'll see reflected in the literature, and it just makes sense then that using ranks to pick which is the best, let's say like the median rank, isn't really a great way of choosing a treatment. We want to account for our uncertainty in that as well, and that's what that measure of sucra tries to do for us. Let's see if there are any other questions. Okay, I don't see any other questions coming through. I hope the midterm exam is going fine. Certainly post your questions if you have any about for clarity to the website. And if there's any questions about the bugs code or anything we've gone through today, again, feel free to post those to the course site, and I'll be happy to answer those. So thanks a lot for tuning in today. We'll have class on Wednesday, and Bill will be leading that class. I think what we'll be talking about is combining aggregate level and patient level data, but I may be wrong. So thanks again, and we'll talk to you later this week.